Hello, in this video I'm going to be introducing several techniques to handle collisions between convex polygons. And I'll even look at handling collisions in a static fashion too. But I've got two things to mention just before we get started. Firstly, anything you can do to a convex polygon, you can also do to a quadrilateral. So those of you with tile-based systems using rectangles and squares, all of this material should be very relevant too. Secondly, it may seem like a horribly complicated thing, convex polygon collision detection, but it isn't. I want to focus on the algorithms rather than the code for this video, and so the coding sections may go a bit quicker than usual. However, I encourage you to download the source file from the GitHub and study it for yourselves. Let's get some of the very basics out of the way first. As my regular viewers will know by now, I draw everything by hand, so technically nothing you'll see on the screen is a polygon. A polygon is defined by points connected by straight edges. And as you can see, I'm no good at drawing straight things on my screen. And what I have here is called a concave polygon. And concave polygons present all sorts of problems I'm not going to discuss in the video, simply because they have something like this. And a concave polygon can be identified because it has at least one internal angle that is greater than 180 degrees. And so for this video, we're not interested in concave polygons, we're interested in convex polygons, which means all of the internal angles are less than 180 degrees. Now I know that a large part of my audience build simple 2D games, and so we mustn't forget that rectangles and squares are also convex polygons. And the algorithms I'm going to show today, there are some explicit optimizations you can make if your system only contains quadrilaterals such as this. But the code I'm going to show is for arbitrary sided convex polygons. However, I just want to get out of the way one little thing which deals with just rectangles only, and you may have heard of it. It's called AABB, which stands for Axis Aligned Bounding Box. And this is an incredibly simple collision detection routine just for squares and rectangles, and specifically for squares and rectangles that haven't been rotated. And this means, given an axis of a world in our x and y directions, the sides of the quadrilateral are parallel to those axes. Checking to see if two axis-aligned quadrilaterals overlap is very trivial. If I label this one P and this one Q, we can intuitively see that in the x-axis, if this side of P is less than this side of Q, and this is just for x-axis, then there is potential for overlap. Because if this highlighted side of P was greater than the right-hand side of Q, clearly they wouldn't be overlapping. We can confirm this with another check, that if this side of P is greater than this side of Q, then in the x-axis these two quadrilaterals are overlapping. And so if I label this as x, and this point is x plus width for that rectangle, and the same applies for Q, we know that there's overlap in the x-axis if px is less than qx plus w and px plus w is greater than qx. And because our quadrilaterals are axis aligned, whatever applies in the x-axis also applies in the y-axis. So we can simply duplicate the formula, replacing x's and w's for y's and h's, h being height of course. I'm not even going to code this up because it's so simple and quite obvious, but I felt it needed a place somewhere in this presentation. As usual, before we get stuck into the algorithms, I'd like to just demonstrate the kind of thing I'm going to be building today. And this is just a little program that demonstrates two alternative methods for detecting overlap between convex polygons. And we can see we've got a selection of convex polygons on the screen. I've got a pentagon, which I can move around. The line from the middle of the pentagon to the outside just helps with the direction, so I know how to steer it. And with the arrow keys, I can move the pentagon around. With the W, A, S, and D keys, I can move the triangle around. I can't move the square around in the bottom corner. And with the function keys, I can choose between 4 different options of the algorithms. The first is called separated axis theorem. And as you'll see, as I move the pentagon into the square, it's changed red. That indicates that overlap has occurred. In fact, I can go over the triangle and the same thing happens. And it's very, very precise. For now, the alternative algorithm, where I look at diagonals versus edges, gives exactly the same result. I can move the triangle into the quadrilateral as well. Detecting whether two polygons overlap is very useful, but if we wanted to actually constrain them from overlapping, we need to apply some sort of static collision resolution. And so I can press F2 to select static for the separated axis theorem version, and we'll see what happens. So I can control the pentagon. We can see it doesn't go between the shapes, but it judders a little bit. I can't force it into the other shapes. Now, the shapes have a degree of priority, so if I push the triangle, I can push the other shape around. But I can't push the quadrilateral around with the triangle. We can see the collision is quite robust. There's no dynamic responses implemented here, so the feel of what's going on may look a little strange, because you'd expect it to rotate and bounce accordingly. This is just static resolution. It's just a way of stopping the shapes from overlapping. The alternative method, using the shape's diagonals, and we will go into some detail about these methods during this video, I feel is a little bit more numerically stable. So if I take the pentagon this time, what we notice is, well, if I set it up, there's actually less juddering as part of the resolution. The diagonal method approach is a little bit more computationally intensive, but fractionally so, but I think the results and the stability are just a little better. So let's get started with the rather traditional separated axis theorem. Here I have a polygon, and here I have another. Firstly, we can see they're both convex, and secondly, we can see they're not axis aligned in any way. This approach involves looking at the shadows of the shape along an axis, and checking if for that axis the shadows overlap. In fact, we're going to check against several different axes. And if the shadows overlap for all of those axes, we know that the two shapes have collided. One overlaps the other. So what are these mythical axes? Well, I'm going to create an axis relative to each edge of each polygon. And I'm going to do that by simply taking the normal of an edge. So taking this edge of this triangle, I'm going to create an axis relative to that normal. Now, it doesn't matter where that axis actually exists in space, as long as we have something that is parallel to it. So I'm going to translate that axis down here. It just makes the drawing a bit clearer. And now I'm interested in the normal to that axis, which is of course the original direction of the edge of the polygon to begin with. And somewhere in space up here, I'm going to turn a light on. And this is a special light because it transmits light globally, but in a single direction. This means that all of our points will cast a shadow onto this axis. And we look at all points on both shapes. For each shape, we then work out the minimum and maximum extent of that shadow. So for the quadrilateral here, we can see the two big red points on the axis. And for our triangle, we've got the two big blue points. We've got the two shadows of the two shapes. And what do we see? Well, the shadows overlap. And using a method very similar to the axis-aligned bounding box I've just described, we can consider that for this particular axis, we've got overlap. And so far, our shapes must be overlapping. This algorithm requires that we repeat this process for every edge of both shapes. In fact, it'll be for every edge of all shapes we want to test collisions between. So let's consider two shapes that are not overlapping, and we'll start with this edge. So we'll take the normal of this edge to create our axis, and this is called the projected axis. I'm not going to translate it this time. I don't need to use the light bulb analogy anymore. I think you can see how we can crush these points onto this axis. When we project the point onto this axis, we can see in this instance there is no overlap between the two shapes. And if we find one axis that has no overlap, then the shapes can't be in collision. They are indeed separated along that axis. Things get a little strange when we try to assign numeric values to what's going on here. But ultimately, the numeric values of things is quite irrelevant because it's all relative to one particular system. So how do we actually do these projections? Well, quite simply, it's just the dot product between two vectors, one of which is our axis of projection, and the other is a vector to the point. Now, these 2 points, naturally, are at 90 degrees to our normal, and when you do the dot product between two vectors, you get a scalar value. In this case, the scalar value is 0, because don't forget, our dot product, in this case, is going to be px times nx plus py times ny. And we've done dot product as projections quite a number of times on this channel. And in the past, I've referred to this method of dot product as being an indication of how similar two vectors are. If I just quickly describe two vectors here, this one is going to 1, 0, and this one is going to 0, 1, and we apply the above formula, we've got 0 times 1 plus 1 times 0, which is 0. The vectors are not similar at all. And this is quite right, because they're at 90 degrees to each other. If, on the other hand, we had a point going to 1, 1, we end up with 1 times 1 plus 1 times 0, clearly a 1. And we can see here, if we were to drop a shadow down from that particular point, of course, the result is 1. This also applies to vectors going in the opposite directions, except this time you have minus signs. And so for this simple polygon, the one outlier is of course this point. And if we take the dot product between this point and the normal, we end up with the projection along the normal axis, our axis of projection. And this gives us some value. Let's call it Q. Naturally, these two other points also were projected in exactly the same way, and they gave us 0 in this case, but that doesn't mean we should ignore them, it just means we've got another pair of values, in this case both equal to 0, which I'll call Q prime. We can then test Q and Q prime to work out what the length of the shadow along the projected vector is. And if the shadow for a particular axis of all points tested between both shapes being tested, if they overlap, then for that axis they're in collision. If for any of the axes we test there is no overlap, then the shapes are not in collision, and we can abort the algorithm. And that's really it. We're taking all of the points, crushing them from 2 dimensions to 1 dimension, and then comparing the extent of those points per shape to see if they overlap. So let's take a look at implementing separated axis theorem in code, but before we can start testing whether polygons overlap, we need some system of actually representing a polygon, manipulating it and drawing it to the screen. And of course I'm going to use the Pixel game engine for this. And as I mentioned at the start of the video, I'm already going to use some code I've created, but I will just talk you through what's going on here. So in the main function, I'm creating a pixel game engine of resolution 256 by 240, and each pixel size is going to be 4 by 4 screen pixels. In the game engine class, I've created a simple struct that represents a point in 2 dimensions. And I've created a simple polygon structure which contains a vector of points, because a polygon can have any number of points. But I've also included a central position point for that polygon and an angle, and I'll use these two variables to transform the shape from the local space of the shape to the world space, and that's what these vectors are. So here is another vector of 2D points, and this is the original model of the shape. This vector P will be updated every frame with the translated version of the model of the shape. And we did exactly this many times for the console game engine, in videos such as Code It Yourself Asteroids and the Code It Yourself Worms series, where we had wireframe models. So we take an original model, use these values to translate that model into world space, and the model in world space is represented by this vector of 2D points. Finally, we've got a flag which represents whether it overlaps, and I'm using that to colour the shapes. I only used 3 shapes for this demonstration, but I could have many, so I'm going to store those in a vector of polygons called vec_shapes. In onUserCreate, I'm going to define my 3 shapes. The first is a pentagon, so that's got 5 sides. And so I loop through all 5 points, and using cosine and sine, I can work out where those points are relative to the origin of the object, 0, 0. I can do exactly the same for a triangle, but this has only got 3 points, of course. So the angle I'm passing in is 2 pi divided by 3. Finally, my third shape is a quadrilateral. And just to be a bit different, I'm handcrafting the coordinates. Again, it's relative to the origin, so this is -30 to +30 around a centre point 0, 0. And when we translate from model space into world space, that origin will be translated to 5200, and we'll rotate the model as necessary depending on the angle value. You'll also notice that I'm pushing these coordinates to the O vector, which represents the original model, but I'm also pushing them to the P vector. That's just to initialize the P vector to the same number of points, and to make sure that the points are the same. Finally, I add the 3 shapes to my vector of shapes. In OnUserUpdate, I've got a little bit of user input code. So this is just to handle the keys. Now I'm using the arrow keys to control shape 1, and I'm using the W, A, S and D keys to control shape 2. If the user presses left or right, or A or D, I just want to increment or decrement the angle for that shape, and I modulate by f-elapsed time to account for variability in the frame rate. If they press the up or down keys, I create a unit vector based upon the angle using cosine and sine, and displace the shape's position by an amount along that unit vector. I scale it to 60 here, which is the equivalent of setting the speed of movement. Of course, if they press up, it goes one way, and if they press down, it goes in the opposite direction. I do exactly the same for shape 2. Once I've got the user input sorted out and I've updated the shape's position, I then need to transform the shape's model into world space. And that's done through this little auto for loop. So I iterate through all of the shapes, and then for each point in the shape's model, I calculate its transformed position. And this is just a combined 2D matrix transform. So we can see here with the cosines and the sines, I'm handling the rotation based on the angle, and I'm offsetting the final position by the center coordinate. I'm also going to take this opportunity, since I'm going through all of the shapes, to set the overlap flags to false. Finally, I want to draw the shapes. So again, I iterate through all of the shapes using a little auto for loop, and I draw a line between successive pairs of points. And I can access these points through the index I. That's why I'm not using an auto loop here, because I know that successive points are I and I plus 1. I just need to be careful though, because I want my shape to be closed, and I don't want to access points that don't exist. So when I'm taking on the neighbouring point, I use the modulus function with the size of the number of points in the point vector. This will ensure it wraps back round and closes the shape for me. Finally, depending on the overlap flag, I choose the colour of the shape. If it is overlapping, I'm going to colour it red, if not, white. It's quite convenient to know what direction the shapes are facing in so you can control them sensibly, so I draw a single line from the middle of the shape to the first point. And that's really it for the startup code. I update the shape's position based on user input, and I draw them to the screen. At the moment, I'm not checking for any overlap, but let's take a look to make sure that this works. So there are my 3 shapes. The arrow keys control shape 1, which was the pentagon, and the W, A, S and D keys control shape 2, which was the triangle. I'm going to create a function called shapeOverlapSeparatedAxisTheorem, and this will return true if the shapes indeed overlap. We're going to pass it 2 Polygon arguments, and this function will return are they overlapping. The algorithm has a lot of repetitive code, and I have to test each edge of both shapes. But I don't want to have lots of repetitive code in this function. I also don't want to do any vector trickery, such as merging the 2 sets of points together. So I'm going to create 2 pointers, poly1 and poly2, and set those to the address of our shapes. And we'll first of all test one shape against the other, then we'll swap these pointers around to test the other shape against the original one. It'll become a bit clearer when we start writing some code. I know that for this function I'm only going to be testing 2 shapes to see if they interact. So I'll create a small for loop just to select each shape. If the shape is 0, I'm happy with poly1 equaling r1, but if the shape is 1, I want to swap them around. So a quick little check for that. Now it doesn't matter which shape poly1 represents, we know we want to go through each edge of that shape and create a projected axis. And in much the same way I drew the shapes, I'm going to use the index of the point in that vector and the index plus 1, of course making sure I wrap around. Using these 2 indices, I can extract the points at the ends of an edge segment on our polygon. So here I've got it for the y-axis and here I've got it for the x-axis. Subtracting these 2 points will of course give me a vector along that edge. However, I want a normal to that edge, and so that's why when I'm constructing my axis projection vector, I'm passing the y's into the x location, and inverting it, and passing the x's into the y location. This will give me a normal to the edge. Firstly, I want to project all of the points of the first polygon onto that axis of projection. But I also want to work out where the minimum and maximum extents of the projection lie. So I'll create two variables, min r1 and max r1. And I've set them to infinity and minus infinity, and you'll see why in a minute. So with the one axis of projection, I'm now going to iterate through all of the points on the first polygon. And I simply calculate the dot product between that point and the axis of projection. This gives me a scalar value, don't forget. Now, instead of storing all of the scalar values for all of the points of the polygon, I am only interested in the minimum and the maximums. So as I go, I'm going to calculate the minimum and the maximum. Once I have the extents of the projection for shape 1, I do exactly the same, but with shape 2. And finally, and this is why I wanted to introduce AABB, in a very similar way, I check to see if those extents overlap. If they do overlap, I just want the loop to continue. If they don't overlap, then the shapes are not colliding. I can abort now and just return false. If, however, I get overlap for all axes, I get to this point and I can return true. The shapes must be overlapping if this is the case. Just a quick little summary of what we're doing. We're going to test two shapes against each other for collision, but we need to test one against the other and then flip them around and test one against the other. This ensures that we create an axis of projection for all edges of both shapes. Once we've got that axis of projection, we take the points for shape 1 and work out where the shadow lies along that axis. Then we take the points for shape 2 and also work out where the shadow lies along that axis, and then we check to see, do the shadows overlap. If there is any axis where the shadows don't overlap, we return false because the shapes are not in collision. However, if on all axes the shape shadows do overlap, then they are in collision, so we return true. All that's left to do now is to call this function. So for the particular shape that I'm testing, I'm going to call our shape overlap separated axis theorem function and pass in the two shapes. One little point about this pair of loops: they're set up in such a way that shapes cannot be tested against themselves. It's also set up in a way that we only test a pair of shapes once. So let's take a look. So I'm going to drive my pentagon into the quadrilateral and we can see the shape turns red. And we can get it, let's have a look how accurate it is. The edges are probably not touching there, but let's just back it up a little bit. There we go, it is quite accurate. So that's very nice. Let's go and test with our triangle. And oh dear, we see it's not overlapping with the triangle. Why is this? Well, simply put, it's because of the order of tests that we're performing. We're basically testing, is the pentagon interacting with the triangle, and then is it interacting with the quadrilateral? And so even though it clearly was overlapping the triangle, when it was tested against the quadrilateral, it returned false, so that reset the overlap flag of our pentagon. So I'm going to just accumulate with a logic OR here. So if any of the shapes cause an overlap with the pentagon, then it remains set. So let's try it now. So we can try our triangle, there we go, it gets set to red, and we can try our quadrilateral, and that gets set to red. Let's also move our triangle around. There we go. Very nice. Depending on your application, you may want to structure the order of collisions in a slightly different manner. It really is application dependent. And so that is separated axis theorem. Now, it's a bit of a bonus 2-for-1 video, this. When I first started thinking about collisions between convex polygons, of course I knew separated axis theorem existed and was readily used by a lot of people. But as a programmer, I feel it's important to try and think about things from first principles sometimes, you know, just to keep the brain ticking over. And so I wanted to develop an algorithm which would give the same effect as separated axis theorem, but approach it from a different perspective. Now, full disclosure, this algorithm that I'm about to show could well exist. It could be used by lots of people. I don't know, I've not researched it, I don't have a name for it. If it does have a formal name, please leave a comment below. But for now, I'm dubbing it diagonals. One of the properties of a convex polygon is nothing can fit inside it. i.e., the boundary of the polygon is equal to its convex hull. In contrast, a concave polygon isn't. The convex hull would require this edge too. Therefore, if I draw a line from the midpoint of the polygon to one of its external points, I'm dubbing these the diagonals, I can be sure that the diagonals never leave the boundary of the polygon. This is not the same, of course, for a concave polygon. If I take some midpoint, that one's fine. Ooh, this one, the diagonal has left the boundary of the shape. Not good. Then this one, then this one, then this one. By knowing that all of the diagonals lie within the boundary of the shape, anything that intersects those diagonals must mean that something has entered the shape. Knowing this, we can test the diagonals of one shape against the edge segments of another. This means we can use a very common line segment intersection algorithm to test the two lines. The output of a line segment intersection algorithm is usually a parametric value that represents the distance along that line, typically normalized, to the location where that intersection occurs. And this is usually denoted by t. So we'll have t1 for that line and t2 for that line. In this instance, t would begin at 0 here and end at 1 here, and begin at 0 here and end at 1 here. And this gives us some incredibly useful information. We know that at this intersection point, along this diagonal, we've intersected with another shape. So we'll call that distance t1. But because we know that the length of this diagonal is always going to be 1, we know how far the diagonal has penetrated the shape. It's simply 1 minus t1. This means we can displace the shape backwards by 1 minus t1 multiplied by the length of that diagonal. Very simply, we can statically resolve that collision. Now, in much the same way as separated axis theorem, once we've tested one shape, we have to flip them around and test the other shape, because we can see in this situation none of the original triangle's diagonals intersect with any of the edges of the second shape. But this time, one of the second shape's diagonals intersects with an edge of the triangle. And depending on how we want the response to work, we can either displace the quadrilateral backwards by this distance, or we can push the triangle forwards by that distance. This will depend on the application. So with this diagonals edge intersect approach, not only do we get overlap information, we also as a byproduct get information on how to statically resolve it. And I feel it's also a little bit more intuitive than doing vector projections, though admittedly not as mathematically clever. So let's code this up. I'm actually just going to copy the method we've already created, because the outline code is pretty much the same. I want to check one shape and then the other, except this time I'm going to call the function diag. I'm going to remove the separated axis theorem component. So in principle, we're going to have two nested for loops. The first is going to check the diagonals of polygon 1 against the edges of polygon 2. Now specifically, I'm interested in line segments, not lines. So a line segment is defined by a start and an end point. And for clarity, I'm going to add these in and label them slightly differently. So for our diagonal, I'm going to take the midpoint of the shape as being the starting point of our line segment, and a point on the boundary of the shape as the end point of the line segment. In much the same way, I'm going to create a line segment that represents the edge of the second shape. This time I'm taking a point from the edge and I'm taking its neighbouring point, remembering to wrap around to close the polygon. I've covered line segment intersections in several other videos, and you can Google it and get it straight away, but this is the equation for it. And this will give me t1 and t2 values. I know that if both my t1 and t2 values lie between 0 and 1, then the line segments are crossing each other. If one of these values is outside of 0 and 1, then the lines are crossing each other, certainly, but not within the boundaries of the line segment start and end points. So if the line segments cross, I'm going to return true. I don't need to do any further tests, I know I've got a collision. If nothing returns true, then I can return false. I know that no segments have crossed each other. And so that's it. It's very simple. We take the diagonal of one shape, test for intersection against the edge of another, and if it returns true, we're going to set the overlap flag of our first shape to true. So where we're testing for overlaps, I'm going to copy that line, paste it in, comment out the first one, and change this to diag. Let's take a look. So we've got our shapes. Pentagon will go down to the quadrilateral. Straight away, it behaves in a very similar way to the separated axis theorem. And it's a little bit beyond my mathematical abilities, but I'm fairly certain you could prove that this is a very accurate method. But let's not forget that because we have generated T1 and T2 values, we've also got the information to resolve this collision statically. Instead of modifying this function, I'm going to copy it and create a new one. And I'm going to call it diag static. So this function will test for collision and try to resolve it. It doesn't matter which polygon we're testing, we will want to create a vector that represents the displacement to set the original polygon's position to get it out of collision. Now the polygons could be overlapping in such a way that there are multiple diagonal and line intersections occurring. If I want to displace the polygon accurately, I don't want to just abandon it at the first attempt. It might detect an intersection and say the shapes are overlapping, but it won't displace it accurately to stop that overlap from occurring. So I'm going to accumulate displacement depending on how many intersections occur. So here we can see the 1 minus t1 value, and I'm going to displace along the diagonal, which we can represent as a vector by subtracting the 2 points at the end of the diagonal's line segment. If we make an assumption that shape 1 is the one we always want to respond to static collisions, then during the first round of tests, the shape pulls itself out of the body it's collided with. But during the second round of tests, the body pushes the shape out. So this displacement vector we need to change the polarity of depending on the order of the pair of shapes we're testing. And so I'm doing that here, using the shape index from our original for loop to determine whether we multiply by -1 or +1, and I directly change the original shape's location. Because we have statically resolved the collision, there is no chance of overlap occurring, so this function now will always return false. Again, let's test the theory. Create a copy, comment that line out, and this time we're going to statically resolve the collision. Let's take a look. I've got my pentagon, I'm going to try and crash it into the quadrilateral. And I can't. The diagonal of the pentagon is pushing into the edge segment of the quadrilateral. Let's try it the other way round, and we'll use the diagonal of the quadrilateral to push into the edge segment of the pentagon. And you can see the static resolver pushes the pentagon out of the way. Again, this comes down to the order of priority. In fact, there's no way I can make these shapes overlap each other. Now, because of the order of priority, successive shapes become more dominant. So here, instead of the triangle being the shape that gets resolved, the pentagon is. But the triangle gets resolved against the quadrilateral. Nothing can move the quadrilateral. Let's park the pentagon down there, and we'll try and shove a wedge in between the two. Very nice. And don't forget, right now the collisions are purely being statically resolved. There's no physics at play here, so they might not resolve in a way that feels quite right. But it seems quite accurate against multiple shapes. I'm pleased with that. I think it's a good idea for programmers to occasionally go back to first principles and try and work out algorithms for themselves. They might not be the most efficient or the most optimal, but it's a very useful thinking exercise. And to be honest, part of the fun of programming. So is it possible to add static collision response to the separated axis theorem? Well, of course it is. Let's start by duplicating the separated axis theorem function, and I'll call this one static. The aim here is to choose the minimum amount of distance that has to be displaced for one of the shapes to get out of collision. The information we have at hand is how much the shapes overlap on their projected axes. So perhaps it makes sense to store the amount of overlap and use the minimum overlap to influence how we displace the shape. So I've created a variable called overlap and set it to a very large number. Once we've worked out the shadow extents of both shapes along the projected axis, we can calculate their overlap, which will give us a scalar value. I'm always keeping the minimum here, so that's why I'm testing against the overlap calculation and the previous value of overlap. We know if at any point this returns false, there is no overlap, so we only need to displace the shape if we get here. There's a variety of ways to displace the shape, but the one I'm going to choose is to displace it along the vector between the two center points of the shapes. And I'm calling that vector D. I'm going to need the length of D so I can normalize it. And I'm simply going to take our overlap value and multiply it by the unit vector between the two shape center points. Again, if we're statically resolving a collision, this function should always return false. There can't be any collisions. Let's test this function. Separated axis theorem, static. Take a look. So let's try our triangle into the pentagon. The order of priorities is still the same as before, so the triangle is the dominant shape. Can the pentagon enter the square? No, it can't. What happens if I try to push the triangle into the square? Well, there was no solution it could find, so the pentagon has gone somewhere, but I don't know where. And so there you have it, a work in progress perhaps, but a variety of methods to handle collisions between convex polygons and quadrilaterals, particularly useful if you're building a top-down city-based car crime game. Anyway, if you've enjoyed this video, a big thumbs up please, have a think about subscribing. The source code is available on GitHub, come and have a chat on the Discord server, and I'll see you next time. Take care.